geez. Oh, okay. Like for just one. So wait, literally, like if I. Ew. No, actually, that's really big. Wait, so if I don't get into micro, what am I supposed to do? Sell Malek? I thought those were only sponges. How does that work? She probably told me about this advisor. Like, if they are the different advisors who want biomakers. Oh, okay. Like, what if they told all of us to go micro? Just fight to the death? What do I do if I can't, if I don't get it? Well, like, there's, no, I guess I do it. But that literally makes it it's fine. I'll be the last to see. I'll be like over the summer, I'll be like refreshing to see like any changes in my life. What? The research, but I haven't like put it together. I still need 2 more sources. That's 5. I do 5. I don't know. Now it's something different.
Okay, chapter 16. I'm really happy we're onto this because 17 and 18 is the last unit and it is basically like an application of this stuff and I love it. I don't know why, it's just fun. So this is just summary notes that we're gonna I'll come back and highlight some key points in here. So we're not gonna go through all these bullet points individually at any point. We're just gonna come back and I'll show you like where it's written down, okay? So what we are talking about today is we are clarifying what we meant about stoichiometry in Chem 1. So when we first talked about stoichiometry, we would give you a chemical reaction and we would say, if I'm given 2 moles of H2 and 1 mole of O2, it will all react and I will all be converted into 2 moles of H2O and none of the reactants will be left over and I will make all of that product. So let me kind of summarize this in a way that, I didn't do this in my other classes, but I think it could be useful. We're gonna use this method as we get further into the chapter. So I'm gonna say initial amounts. Let's pretend we actually have 2 moles and 1 mole, just to keep things simple, like matching the stoichiometry. So we start off with no water, but we have hydrogen and oxygen. And then at the end, we told you before that we used all those up and made 2 moles of this. And in some chemical reactions, that is true, that everything ends up getting turned into product. There are also ways that even if the chemical reaction doesn't want to do this on its own, we can kind of force it. That's what we talk about at the end of the chapter, Le Chatelier's principle. That's forcing a reaction, manipulating it to get it to go all the way to products. But the thing that's odd is that this isn't actually how a lot of chemical reactions occur. they actually have a balance point between products and reactants that isn't zero reactants and all products. So I'm gonna do this thing with my hands for probably the whole chapter to talk about balance point, okay? So the way I've shown it here and the way we talked about it in Chem 1 is we started with lots of reactants, we had no products, and then they just flipped. And there was nothing left over, and there was lots of product made, right? But in reality, sometimes there is some reactant left over. So the most simple example of this is when we looked at those charts with the salts and the like different solubilities at different temperatures. If you remember, I'm gonna make it up, but I think it's right. I think we said at 0 degrees C, we could dissolve like 15 grams of potassium nitrate. So dissolving, if you want to write that as a reaction, it would be the solid forming aqueous potassium ions and aqueous nitrate ions. Aqueous, remember, just means they're surrounded by the water. Okay? Well, if I add, let's say 25 grams of potassium nitrate, so I'm not going to talk in moles, I'm going to talk in grams for a second because that's what we used before. So I have 25 grams of potassium nitrate and I have none of the ions yet, and it's at 0 degrees C. That chart told me that only 15 grams of it would dissolve. So 15 grams of it dissolves and makes some ions, but guess what? I still have 10 grams of the potassium nitrate left over. It does not matter what I try to do, as long as I don't change the temperature. I can't force that additional 10 grams to turn into the products. So there is a balance point that is not 0 of one and all of the other. There's this balance point between the products and the reactants. And that balance point is called equilibrium. So you can think of it like a scale. They aren't equal to each other. They are, they're equal to whatever the balance point is for that particular chemical reaction. Like a different salt might have a different balance point.
So are you saying there's a balance when there's 10 grams of CN03 and 15 grams of the...
Well, 15 grams has dissolved, so you wouldn't know the exact, I guess it would be the same mass, but they'd be surrounded by water. But yeah, so if we start with 25 grams, only 15 of it is going to turn into the ions, and there's going to be some of that reactant left over.
And that's where the equilibrium...
That would be the equilibrium point, yeah. And even if you just sit there and watch it for an hour, that's not going to change. You're still going to, even if you try to stir it up, right? You're still going to have 10 grams left over that you can't seem to make them make product. Okay, so let's do an example that's like a little bit more chemical-y. So our reaction here is hydrogen gas, iodine gas, forming hydrogen iodide. Pretty straightforward chemical reaction. 2 moles of things turn into 2 moles of something else. Okay, 1 and 1 turn into 2. And these images are showing us the reaction progress. So at the very first one, we're just adding reactants. We haven't let any time elapse. So there's no products that have been made yet. And then as the clock moves around, we're saying a little bit of time passes, a little bit of time passes, a little bit of time passes. What happens? Okay? So I want you to take a minute or two, look at it on your own, talk to your neighbor, and think about what is happening as we move from A to B to C to D. And what might be useful is to like count up each of the chemicals and figure out, how much of them there are in each of those pictures. Okay? Okay, so let's just talk about what we would have thought of would have happened in Chem 1 with A before we look at what goes on. So they're exact stoichiometric ratios, right? The ratio in the equation is 1-to-1 for the reactants, and we have a 1-to-1 ratio for the HI and the I2, right? This image shows 8 molecules of each. So like if we were in Chem 1, we would say, okay, I've got 8 molecules of H2. We could pick either one because there's no limiting reactant here. And for every 1 molecule, I'm going to make 2 molecules of HI. And I would assume that that means that I could make 16 total molecules of HI, right? But what the reaction is showing us is that as a little bit of time passes, those chemicals start to react. Now, we skipped over this in 15 where we talk about what has to happen for chemicals to react. They have to hit each other. So they're bouncing around. They have to have a collision. The collision has to have enough energy to break those bonds, and it has to be in the right orientation. So like, you know, maybe my thumbs are the hydrogens, and, oh wait, no, that would be HI. Okay, maybe this is the iodine, and this is the 2 hydrogens. And so they bang into each other, and one of each pairs with the other and forms 2 of those HIs. Okay, so we've said that after this, from A to B, that's happened twice. So 2 molecules of H2 and 2 molecules of I2 bumped into each other and formed 4 molecules of HI. Okay, and then as we progress to C, that happened again. We get another 2 of each, forming 4 more, so we get a total of 8. Then we move on to D, and nothing's changed. And if we went even further, if we sat there and waited, we'd still see 8 molecules of HI and 4 of each of the reactants. So we've hit that balance point for this particular equation. So we won't actually be able to make 16 moles. We don't know how to predict yet how much we're going to make, but it's telling us this is the balance point that we hit. Another way of we'll skip over that for a second. Another way of visualizing this is to say, I'm not that tall, I'll pull this down here, is to say we start with none of the products. Now in this one they separate them, they're not exactly 4 or 8 and 8, okay? They don't start the exact same amounts, but the idea is the same. So you've got none of the products who have lots of reactant. As the reaction goes on, the reactant gets converted to products. So this one's going down and this one's going up, right? This should make sense. We're making product, we're using reactant, and then we hit this point and we see no change in the concentration. And no matter how long we sit there, we're not going to see any change in the amounts of the reactants and products. But notice the reactants are not 0, okay? There is a balance point here that it has stopped at. So in that previous one, so here's my reactants and here's my products. So they start at 0, they move, and then they hit this balance point and they stop. It does not go all the way to 0 in 16. It stops at 4 of each of these guys and 8 of the products. And that's true of every chemical reaction, that it has a balance point. The ones that we looked at in Chem 1, we were assuming that their balance point was so far to the product side that we just pretended like there were no reactants whatsoever left over. And there are certain conditions you can set to make that happen. So this wasn't like a bad assumption. We just were being very picky about which examples we used. But there are lots and lots and lots of chemical reactions where it is not going to go all the way to 0 reactants and 100% product. There is a balance point. Okay? So that balance point is called equilibrium. When we get to that balance point, and you can identify it because you don't see any changes in the amounts. That's what's being represented by the fact that, they're horizontal lines. There's no changes in the amounts at this point. Concentration of reactants and products no longer change. Okay, it's important to note though that even though we don't see a change in the amounts, there's actually a lot of reaction still happening. It's just that the reaction happens in both directions. So what do I mean by that? The H2 and the I2, they are still bumping around. They're still hitting each other, which means they probably are still going to make some HI. Also, though, that HI is going to bump into itself and turn back into H2 and I2. The way that we write this, though, when we're talking about a chemical reaction, is we write a double-headed arrow. I guess they're two arrows. I don't know. This is how we write it. I don't know how you want to describe that. There's these little like half arrows. You don't really see it like this, but that's what it's mimicking. We're trying to say that the reaction can go forward. I2 and H2 can form HI, so this way. But at the same time, the reaction is also going backwards, and the HIs are reacting backwards to form I2 and H2. That's also a totally new idea. You're like, what are you talking about? How can products turn back into reactants? There's no reason why they can't. And if there is an optimum balance point here, if those reactants start to make more products, and there's some balance point, I mean, that balance point comes from potential energy. You don't really need to know why or how. Just know that there is a balance point that optimizes potential energy. So if I try to make the reaction, or if the reaction itself goes forward and makes more reactant or more products and less reactants, the products are just going to turn around and start reacting to bring it back to that balance point. So this is what's meant by dynamic equilibrium. When we are at that balance point, it's not that all reactions stop. It's that both reactions happen at the same rate. So you're getting forward reaction, maybe, like 10 times per second. It's obviously a lot higher than that, but like, let's say there's 10 molecules each turning into 20 HIs. You're going to get the same 10 reactions happening the other direction too. So the overall amounts don't change, even though there's reaction occurring. The analogy they give in the textbook is like migration, which I don't really know why they do that, because I don't know of any country that has like stable population. And then you add in like, babies being born and stuff. Anyway, whatever. We'll talk about it. Let's pretend you've got these two countries and there's, 1 million people in country A and like hardly any people in country B. So people start moving to country B. And then you get to this point where, let's say you have 1 million in country A. Oh, I said 1 million. Okay, so now I need to change it. So let's say you have 750 now in country A and 250,000 in country B. Okay? And maybe people keep moving back and forth between the countries, but you see a stable population. You still see the, whatever I said, 750 and 250. Okay? That doesn't mean that nobody's moving. It just means that they're moving at the same rates. So some people are moving into A, some people are moving out of A. All right? So there's still lots going on, but we see it as no change in concentration. Okay, so I said every reaction has a balance point. So we need to talk about what that balance point is. It's a number that is a ratio of the products to reactants. So think like if they were the same, that would be like a 1-to-1 ratio, or like 50% reactants, 50% products. If they were like this, maybe it's like 25% reactants and 75% products. Or maybe it's like this, and it's 10% products and 90% reactants. There's some ratio between them, right? So that is summarized by a number called the equilibrium constant. And it has the symbol of a capital K. Rate constants, like how fast a reaction happens, is a lowercase k. So this is, make sure it's capital. And it has a clearly defined way that we calculate it. So if you go back to that summary page, it's right here. So it is K is equal to either the molarity or the pressure. So we'll talk about that in a second, but it's some amount of the products, and they're raised to the coefficient from the balanced equation. And then that is over the molarity or pressure of the reactants raised to their coefficients. So products raised to their coefficients over reactants raised to their coefficients. Okay, so let's go back and look at the one that we had here. It's like the same reaction, but they substituted in bromine now for iodine for some reason. Okay, so just from the chemical equation, I'm not going to put numbers in here because I don't have any numbers yet. I'm just going to put it in symbolically. So for this equation, and before I do that, I need to clarify a couple things. So when we do concentrations, it's technically a Kc. So you'll see K with a little c subscript. If it doesn't have a subscript, it is the concentration one. That is way more common. So I'll put in parentheses just K. All right? And so that's concentration, and we would measure the amounts in molarity. And the way we write that is with little brackets. So if I put X with brackets around it, I mean the molarity of X. I don't know if we've done that yet. Maybe we did it? No? Okay. The other way we can do it is Kp, which is pressure. And that would be in atmospheres. And the way we write that symbol is just like a big P with the chemical species as a subscript. So the pressure of X. So in this one, we're going to assume they're talking about Kc because they didn't give us a subscript. So we are going to write the molarity of the products raised to their coefficients over the molarity of the reactants. And it's like the reactants, if there's two of them, they're times each other. So the molarity of H2 times the molarity of Br2 on the denominator. And then the product raised to its coefficient there. So H2 and Br2 are 1, so we don't have to do anything with those. But we're going to square HBr's concentration. Okay, so this is all symbols yet, and there aren't any numbers in here. So lots of these values, these like, you can think of them as a ratio or a fraction or just a balance, you know, where that balance point is. A lot of those are well known. So like I could easily Google this and find out what the K is for hydrogen and bromine combining to form HBr. If I did the reaction and then I measured the concentrations at equilibrium, I could also plug them into this to determine the K. So we'll do one of those problems in a few minutes to like actually put numbers in and calculate stuff out. But before we do that, I want to talk like conceptually about what the size of the K means, because it tells you, like I said, something about that balance point. I've said that like a bunch of different times, but there it is in STARD. It's a ratio unique to each chemical reaction, tells us that balance point, that distribution. Okay, so we're gonna look at these two examples. The one we just did, the H2Br2 forming HBr, and then a really similar one, N2 and O2 forming NO. Okay, these pictures on the side are descriptions, supposed to be descriptions of them at equilibrium. So we've reacted it, it's now hit its balance point and the amounts aren't changing. And we want to get a sense of what the K is and how it compares to the amounts of products and reactants at equilibrium. Okay, we're going to talk a lot about a large or small K. Think of the break point as 1. So if things are like significantly less than 1, so let's say like a tenth, 0.01 or 0.1 rather, or smaller. So the further you get away from 1, we're going to call that small. And then we're going to say that slightly or significantly more than 1 is large. And these numbers, K values, can be like, there's 10 to the negative 14th on the small end, and on the large end, probably just the same, 10 to the 14th, or like I know I've seen ones recently, 10 to the 8th. Okay, so multiple millions or super, super, super teeny tiny fractions. Okay, I want you to count up the number of each species, and let's pretend that each one of these represents a mole, and let's pretend that these containers are 1 liter. All right, so basically the number of them that are shown is going to tell us the molarity of that amount. And I want you to plug those numbers into the K expression and find out what the actual value of the K would be. So, for example, NO, there's 2 of them shown in this picture. There's 1, 2, 3, 4, 5, 6 N2s and 4 O2s. So plug those values into the K and then do the same thing for HBr. Okay, so We get a relatively large number for the bottom one and a relatively small number for the top. No, you're right, 81, because 9 times 9 is, 81, not 18. 9 times 2 is. Thank you. Okay, so bigger number now for the bottom one, relatively small for the top. And what does that tell us about the amount of products versus reactants? Well, when we look at the picture on the top one, there are not very many products, right? Lots of reactant left over, not a whole lot of product. So the reason why that number comes out to be small is because you have a small number up here and a big number down there. So like I even did this in my other class. I was like, okay, 4 over 24 or 1/6, right? Small number on top, big number on bottom. That's going to give you something less than 1. So the products are the things on top. So if I have lots of product, like in the bottom example, so it's big up here and not very much down here, then I'm going to get a big number. So because of how we define the K, products on top, reactants on bottom, if the number is large, that tells us that the reaction is favored towards the products. So the balance point is on the product side. And the bigger it is, the bigger the balance point is over on the product side. And for a small number, the balance point, if it's small, that means it's on the reactant side. And the smaller the number, the more it's favored towards the reactants. That's the terms we use: product favored, reactant favored.
Is that squared dependent on how many of the product there is? If there's like 3 HBr, would it be HBr cubed?
Yes, only if based on the balanced equation.
Okay.
Yep.
Would that be the same thing if there was like 2H2, would it be H2 squared over y?
Yes. Yep, whatever the coefficients are. So, 3x plus y forming 2z. I don't know why I didn't give myself any space for that. So that would be z squared, concentration of z squared, over x cubed y. Okay, let me highlight on that summary sheet what I just said about the size of the K and what it means. Okay, so that's this point here. So how big it is, if it's really small, that's large, really large, it's gonna tell us that the products are gonna be the dominant thing. We often say product favored. Oh, that's not gonna work. Product favored. Okay, if the K is really small, that's an indicator that it's reactant favored. Again, we're just saying, what is that balance point? Is it 10%, 90%? Is it 50-50? Is it 75-25? Okay, we will manipulate Ks occasionally, and the rules for when you manipulate an equation are different than when we did enthalpy. So if you remember enthalpies, like when we flipped the equation around, that would change the sign, okay? That's not the case here. When you flip it around, so these are all summarized right here, and we're gonna use them. I might even just wait to practice them later on, but I want to talk about them right now since we're here. So when you reverse the reaction, you're going to do 1 over the K. So for example, if you had A goes to B and the K was 10, then if you turn that around and say what is the K for B goes to A, it's 1 over 10. This one we're not going to worry about because you're never going to see that. And then if you multiply by a coefficient, so remember like when we did Hess's law, if we multiplied everything through by 2, then you would multiply the enthalpy by 2. In this one, you don't multiply it by 2, you raise it to 2. So in the example here, if I had 2a goes to 2b, then that would be 10 squared for that k. Good? You'll just have to come back to these and review them when we do some practice with them. And then the last thing is KP and KC. So like we said, KP is pressures, KC is concentrations. We can measure gases in concentration though, because concentration is just moles per liter. So it's very normal to know a volume of a gas and know the number of moles. So we used to think of concentration as like something exclusive to solutions, but it is not that uncommon to use it for gases. So it's good to be able to move between KPs and KCs though, depending on whether you know the pressure or the concentration. So this equation allows you to do that, and there's an error here, so I need you guys to change it. The parentheses should be around the RT. And this one, we're going to need to do an example of it for you guys to know what this means, this change in the number of moles of gas. So we'll do an example of that right now. Okay, last rule to keep in mind with Ks is that only gases and aqueous solutions are included in the K expression. Solids and pure liquids, so like when we did the KNO3, you would not include that in the K expression. The K for this would just be K plus times NO3 minus. That's because there isn't a concentration for a solid, right? If it's a solid, it's not dissolved into something, then it doesn't have a concentration. Same thing with a liquid. If it's pure water, there is no concentration associated with that, or pressure for that matter. So you don't include solids and liquids, pure solids and liquids. So just look at the state. If it's an S or an L, don't put it in your K expression. You want to include a gas or aqueous. Okay, let's do one of these KP, KC conversions. So I'm going to pull that equation so we can talk about how to do that change in the number of moles of gas. Go down, down, down here. All right. Difference between KP and KC, we talked about this. This is pressure measured in atmospheres. KC is concentration measured in molarity. The equation that we just looked at, KP equals, is on your equation sheet. I think it's on there correctly with the parenthesis in the right place. So that delta N, that is change in the number of moles of gas. And we mean change over the reaction. So like the number of moles of gas in the products minus the number of moles of gas in the reactants. So for this equation down here, you've got just 1 mole of gas in the product side, and you've got 1, 2, 3 in the reactant side. So it's going to be 1 minus 3 or negative 2 for this example. So what you're doing is you're basically like using the ideal gas law to convert between concentrations and pressures. It's just in a, like summarized in an equation, so you don't have to do it, you know, like think through every individual step. I swear I get one of those Spirit Store emails every day. Obviously I need to unsubscribe or something. I'm like, are people buying sweatshirts every day? Leave me alone. Okay, so let's go ahead and do that equation for this one. They give us the KP here and they want the KC. So do it on your own. I'll start it in 30 seconds or so up here so you can see. But you're just converting between the two using that equation above. And I didn't say this. R, since we're talking about gases, this is the gas constant, 0.0821. And T is in Kelvin. Just like we would do anytime we're doing gases. I'm going to go unsubscribe right now because it's just so annoying. You send too many emails. Yes, that is the reason why I am unsubscribing. Pretty straightforward algebra. Pretty much just make sure that either you know if it's the KP or KC and then your thing is in the right units, atmospheres or molarity. But you may need to convert on some of these. All right, I'm gonna do this one at the beginning of class, but before we're done, I want you to do 1 or 2 simple K calculations. So don't get stressed by, you know what, let's not do this one. Let's do this one. Let's just do one of them and let's do this one. Yes, okay, I'm not even gonna introduce it. I think you guys can do this one all on your own. You're determining the pressure of COCl2 at equilibrium. Okay, so very straightforward algebra. You know the K, so you write the K expression and then just plug in. Obviously, there's going to be more complicated ones. Like if that was squared, you're going to have to take the square root. We're going to get into more, basically doing stoichiometry with this. And at one point, we will have to use the quadratic formula. Do you guys remember the song? X equals negative b plus or minus the square root. Yeah. Can't memorize it without a song. Anyway. All right. I'll see you guys on Wednesday. That's just mean, trying to make you memorize that without a song.
I know the preamble of the Constitution.
That's impressive. I don't.
Schoolhouse Rock.
Oh, well, yes. Okay. I'm just a bill. Yeah. I was singing that to my kids recently to be like, see, we don't have a king, and you actually have to go through Congress to pass laws. Why did you not want to meet today? You're just not ready?
Yeah, I just
Okay.
wasn't.
Okay.
I wouldn't have been ready.
That's fine. Totally fine. You too. Question for me? Oh, let me turn that off. It's like so.
I was gonna wait till today to ask you, but then Chris told me right over there. So I was
Okay.
having trouble to get in for the last week. 'Cause every
Okay.
time I was going in.
So, have you been going straight to the Pearson website, or do you go through Blackboard?
I was going through the Pearson website,
Yes.
but then
I don't know why it was doing that to me. So go to Blackboard and let's see if it fixes it.
Chris just told me I did it in a different browser and it just completely worked. And now I felt really stupid.
That's okay. If you do the homework tonight, just send me an email,
I'll get
even
those
if it's
stuff.
like tomorrow morning or something, because
Sounds good.
obviously if you haven't been doing it for a week.
All right.
But yeah, just send me an email and I'll
Thank you.
take the late points off. Yep.